Dear students, we're currently in the architecture part of this lecture on architecture and programming models for GPUs and coprocessors. In the last session, we discussed what I call the asynchronous host interface. That is, we basically discussed the interface that commands that are issued by our graphics application goes through between the host CPU and the GPU. And we learned that on the host side, the driver and runtime are responsible. And we learned how those two entities are organized, and that there are parts of the driver that are supplied by the vendor, and that there are also other parts that are supplied by the operating system. And we also learned about the command processor that on the other side, like on the GPU side, takes over those commands and distributes them to the functional units that are responsible for processing the commands. So that is, we're now really on the GPU, and we can now discuss the architecture that the commands go through, and we will discuss this architecture in the light of what is currently implemented on GPUs, like nowadays. And we will base this discussion on what I call the graphics pipeline. And we already saw the graphics pipeline. We saw this stacked diagram of the graphics pipeline, which really is the algorithm rasterization 2. And the graphics pipeline consists of a number of stages. And we will now discuss this stage by stage. And we will start with what is called the Vertex stage. And you will recall from our discussion during the computer graphics part of the lecture that the vertex stage is basically comprised of transforming vertices. That is, in the very simplest case, on the vertex stage, what happens are just matrix vector multiplications. Like, we have our affine transformations, like the model and view transform, and we assumed for simplicity that those are basically just one transformation. And we also have our projection matrix, like the matrix that expresses the intrinsic parameters of the camera, and we apply those transformations to all the vertices. And basically, this results just in a bunch of matrix vector products, like where we transform the vertex positions, where we transform the normals, where we maybe transform certain attributes. And in the very simplest case, that is just it. Like in the more complicated phase of a programmable vertex stage, which is what we have nowadays on GPUs, we have a program that is supplied by the user, and that program can do pretty much what the user wants it to do. Like, there's like some arbitrary control flow in that program, in the vertex shader, and that means in general this stage can be like arbitrarily complicated. We generally have a one-to-one mapping. Like, we're providing the vertex stage with a bunch of vertices, and that bunch of vertices is just being transformed, and the stage will not output any additional vertices, like any additional geometry. Like, we're ignoring what would be called the geometry stage or the tessellation stage, and we also ignore newer shader types, like for instance the mesh shaders that were introduced by NVIDIA. And thus we were assuming that there's just a one-to-one mapping of input to output. So the exact same number of vertices that enter the vertex stage will also leave the vertex stage. In general, things are, however, more complicated. Like, the input provided to the vertex stage is usually not just a bunch of vertices, like a stream of vertices, but instead those vertices are usually either instanced or they are indexed. So the concept behind instancing is actually a fairly simple one. Like, consider we have those 4 triangles, and those 4 triangles are, of course, composed of 3 vertices each. But as a matter of fact, the triangles actually share vertices. Like, this vertex V1 here, for instance, is shared. And as the vertices are shared, we therefore generally have fewer vertices than just the number of triangles times 3. And one way to express this type of geometry, like this mesh, would be to just duplicate all the vertices, like have one vertex per vertex in a triangle. So then we would have like a huge vertex stream of independent vertices. But this is not what we in reality do, because in reality, we would rather, for this type of geometry here, just create 6 vertices, like the vertices that I'm showing here, and then use what is called an index buffer to describe the relationship of the different vertices. Like, we would have a vertex buffer that would contain the vertices of the geometry here. And then we would have an index buffer that would have 3 indexes per triangle, and like the first triplet of indices would just be 0, 1, 5 to express that's the 0th and the 1st and the 5th vertex together form a triangle. And then we would have for each triangle such a triplet of indices, and those indices would describe how the vertices map to triangles. And as you can share, like the vertex v1 here is shared by 3 triangles, like in the same way that we also can see this in the illustration. And the idea here is, of course, that we are able to save bandwidth. Like in particular, what we save is PCI Express bandwidth. And the interconnect between the host CPU and the GPU is usually a limiting factor. So this is what we want to do. We want to save PCI Express bandwidth. And on the other hand, there is also the perspective of saving some memory on the GPU side. Like this index format will usually result in a bit of compression. Like in particular, as a vertex will usually be stored with at least 3 floats for the position, 3 floating point numbers for a normal, and 2 floating point numbers for a texture coordinate. And then there are probably also more vertex attributes. And it's of course much more lightweight to just store a single index. It's important to note that this type of indexing only works if the vertices also share attributes. Like for instance, if this vertex v1 would have different normals, depending on if it belongs to this triangle here or to that triangle up here, then we would actually have to like duplicate it on the application side and make it 2 different vertices. Then we wouldn't be able to share it. So this type of sharing actually only works when the attributes are the same, when the attributes are also shared. When we have different attributes with the current graphics APIs, we would have to make this 2 vertices actually. So, and another way of basically compressing data, of making better use of the available GPU memory and of the available PCI Express bandwidth is so-called instancing that we will now very briefly discuss. And that also makes the input assembly phase and thus the vertex stage a bit more complicated than just taking a input stream and passing it to the vertex stage and the vertex shaders. So quite typical examples for instancing are those where we have like large outdoor scenes, and those outdoor scenes have like very complex geometry, like for instance due to high detail that is used for foliage and leaves and grass. Like for instance, if we take this outdoor scene here, this is a typical scene where people use instancing, and if we analyze this scene, then we will find that those leaves here, for instance, are like a bunch of instances, like 4 or 5 instances of the same type of leaf. And then those instances are basically just replicated. So we'll not have a geometry and individual triangles for each of those leaves, where each of those leaves actually has like a bit of complexity associated with it. So the geometric complexity of each of those leaves is relatively high. And if we were just to replicate those leaves across the whole scene, then the geometry in general would be quite complex, because this would result in really many individual triangles and thus in many individual vertices. And in order to avoid that, people use instancing. And instancing would basically just work as follows. So just imagine that we have our relatively complex geometry. Like imagine that this is like a leaf or something. And the leaf is like comprised of a bunch of vertices. And we now want to replicate that leaf. Like we'll distribute that same leaf over our 3-dimensional scene. And that basically sees us on the one hand translating the leaf, like having a translation that repositions the leaf itself and thus all the vertices of the leaf. And we would also usually like rotate the leaf a bit, maybe scale it a bit. So we'll basically take all the leaf's vertices and transform them so that they are in a different position and have a different orientation. And when we perform instancing, we basically do this by not really copying all the vertices and transforming them, but instead we just store all the information that would be required to do so later and at runtime on the fly. So what we're basically doing is instead of storing another object that contains all the vertices with all its attributes, we would just store a pointer to the whole geometry, like a pointer to the leaf. And along with that pointer, we would just store a 4x4 matrix. And that pointer and matrix would basically be our instance. And we would obviously do this for all the leaves and for all the complex geometries that we want to instance. And this, of course, additionally adds to the complexity of the input data to the vertex stage. That is not very different to the simplified input that we had with the rasterization 2 algorithm, where we just assumed that the input were just triplets of vertices. So, and that basically means that on the vertex stage, we first have what is called the input assembly phase that would just take that relatively heterogeneous input, like the input from the index buffer and also the input from the instancing buffers, and would assemble that input and turn it into a bunch of vertices. And this is basically done by just duplicating all the vertices on the GPU side. That doesn't necessarily mean that there is like a second copy in DDR memory of all the vertices, but the way that the vertices go through the pipeline is that the vertices are duplicated. So think of it like a buffer, for instance. Like as soon as a bunch of vertices enters the vertex stage, like the vertex shader, before that the vertices are duplicated. The problem is really in the way that buffering happens with the input assembly stage. What makes things much more complicated is the fact that as those vertices are potentially shared, the GPUs obviously employ something that is called a post-transform cache. That is, when a vertex is really shared, we'll try to not transform it more often than we have to. Like when we have a shared vertex, and that vertex is shared by, say, 3 triangles, then what we strive for is take that vertex and transform it only once, like apply the camera transformation and the vertex shader only once. And then when we encounter that vertex again, but now as belonging to a different triangle, we won't apply those costly transformations again, like would run the vertex shader over it again, but we instead would try to put that transformed vertex in a cache, and this cache would be the so-called post-transform cache. And then when we encounter it again, we would just reuse it. And this, of course, makes things much more complicated because, like in the early days when we had only fixed function execution, then the size of a vertex was pretty much fixed. Like there weren't any user-defined attributes that were associated with the vertex, and it was clear, like of course this depended on the implementation, but the implementation could predetermine basically the size of the class vertex, so the structure that is used to store a vertex. Like the GPU architects, they knew in advance that a vertex would be like a position and a normal and a texture coordinate, and that is it. So, and therefore they could also design the cache around a fixed size data structure. And then they could determine how many vertices would fit into the post-transform cache. So, and the problem today is that we have a variable number of per vertex attributes. That is, the user can supply additional buffers with vertex attributes. And therefore, if we want to cache those transformed vertices, things are more complicated because we don't know in advance how big a vertex will actually be, how much memory it will occupy. And that, of course, makes the design of such a cache relatively complicated. Yeah, and what really adds to the complexity of those post-transform caches is the ensuing primitive assembly phase, where you have the buffer of assembled primitives, and you, on the one hand, fill that buffer from both the vertex phase, like from the vertex processors, and on the other hand, you also have to fill the buffer from the vertex cache. And this is part of what makes this type of cache relatively complicated. And the other part that makes the hardware relatively complex is the fact that it's in order to determine if 2 vertices are the same, we have to compare them attribute by attribute. So equality is determined based on comparing attributes. And this is another reason for this type of design being relatively complicated. But on the other hand, like the post-transform cache is actually a pretty important part of that whole pipeline. Like the order in which the user passes vertices and triangles to the GPU, like the way that the vertex buffers are composed and that the index buffers are composed, have an influence on the performance of the rendering phase. And therefore, there are like a bunch of algorithms out there and different implementations of those algorithms that run over meshes, that come from like a 3D modeling software, and optimize those meshes so that the order of the vertices and of the indices is more friendly towards the post-transform cache. Like those algorithms and those implementations usually use some types of heuristics because it's not very well documented how the post-transform cache actually works. Like the size is usually not very well documented, and the internal execution model isn't very well documented either. But suffice it to say that it's a non-negligible part of the Vertex stage and that people actually optimize for. So we have this part of the Vertex stage, like the input assembly phase, and the input assembly phase has to do with connectivity of vertices and has to do with how vertices are being processed, like with the order, and that vertices are being processed, and that then eventually they will, after they were processed, they'll end up in a cache and can then be passed on to the primitive assembly phase. And we'll now talk a little bit about the execution, like inside this black box. And we already said that when our vertices come in, like they have this connectivity, and then they are basically like the connectivity is resolved. Like the index buffer is pretty much being unrolled, so to say, and we end up with the indices basically being removed, and then only raw vertices going into the vertex processing phase. And then after they have been processed, they might end up in the cache, and then we have the problem that we also have to disambiguate if they are same, and for that we have to like compare them by their attributes. But we'll now talk a little bit about what happens inside that black box. So in the execution model that we're going to discuss in the following is that of GPUs as we know them nowadays. And what I'm depicting here is a single, what I call a vertex processor. But as a matter of fact, this is actually a unified shader processor. So this is actually the same type of processor that would also be used like for fragment processing, for instance, or like in order to execute a compute shader. And we usually like have a bunch of them, like with the architectures that we have nowadays. We usually like have a bunch of them, and we will call that from our discussion on the historical development of GPUs. And we know that the architectures like at a number of those blocks, and inside each of those blocks, we have on those processors we have what is called a core or a shader core. And the shader core uses a programming model that NVIDIA calls SIMT, which means single instruction, multiple thread, and which is a fancy way of saying that the core executes like a number of threads, and it does so in lockstep. Like there are like certain characteristics to this execution model that on the one hand make it very similar to SIMD, and on the other hand also differentiated from SIMD. And like each of those cores on its own can execute a number of threads at the same time, and then we have like a bunch of those cores per processor, and we also have a bunch of processors. And that, of course, adds up to like massive parallelism. Like we can run hundreds to thousands of threads at the same time. So then we're given like our shader, like our vertex shader, and like as a matter of fact, this could also be a fragment shader, but we're currently discussing the vertex stage, so this is a vertex shader. And then we have like a functional unit on the GPU that is called the scheduler, and the scheduler will now try to execute this shader program on the vertex processor and on the cores. And the logical unit that is used to execute those shader instructions is called a warp. That is, whenever we execute those instructions, the shader instructions aren't like executed for individual vertices, but they are in fact executed like for a bunch of vertices at the same time. Like usually those threads that together form a thread group or a warp, they execute like a bunch of instructions from the shader, and they do so for not only a single vertex, but for a group of vertex. Like quite typically, we process like 32 or 64 vertices at once. Like those are typical numbers for current generation NVIDIA GPUs, like on the order of 32 to 64. And the logical execution unit here is the so-called, NVIDIA calls it warp, and other APIs call them thread groups. And the principle here is that those threads execute those instructions in lockstep, and that makes them similar to SIMD, that we discussed when we talked about CPU architectures. And on the other hand, the lockstep and SIMD execution model here are implicit. That is, the instructions that we deal with aren't SIMD, like we don't deal with SIMD registers, but we instead deal with scalar registers. But nevertheless, those warps, they execute in lockstep, and whenever there's an instruction that takes longer than the other threads in the warp, they have to wait. And also, like when there is branching, that actually causes threads that don't take the branch, that don't go into that branch, cause them to wait. Like in a SIMD execution model, we would basically just mask out those threads until the branch was executed. And in the SIMT execution model, this happens implicitly, like implicitly inside the programming model. And the GPU will take care of that, and the scheduler will take care of that. But nevertheless, threads that are inactive, they cannot do anything meaningful. Like inside that warp, they basically are like a dead resource. So we have this execution model with those warps, and those warps, the granularity that they operate in is like a handful of instructions, like the GPU scheduler that sits over everything and distributes the work will basically take like a handful, like 4 or like a couple more maybe instructions and schedule them using those warps, and it will actually schedule them on one of those shader cores. And now those instructions that are being executed, and we usually don't execute the whole shader at once, but we take a couple of those instructions and execute them inside the warp and on those shader cores. And some of those instructions might actually have a relatively high latency, like for instance when we have memory accesses. And when the GPU scheduler, or when the GPU encounters that there are instructions that have relatively high latency, then the scheduler will basically take that warp and will perform a context switch and will make the warp temporarily inactive until the memory access or whatever latency intensive instruction is being executed, until this was served and the operation returned. So whenever this is encountered, the scheduler will make the warp inactive, and that allows the scheduler to schedule another warp during that time. So while the one warp performs like a memory access and waits for the memory to become available, a completely unrelated warp, like for instance from another shader execution even, or like even from another program, can be scheduled on that shader core. And this is actually very powerful because that effectively allows the GPU to hide latency. Like when there is latency for DDR memory accesses, for instance, then the effectiveness of latency hiding depends on how much other warps there are that can at the same time perform some arithmetic, like some additions or multiplications that have way fewer latency. And say you have a warp that takes 100 clock cycles to access memory, and then we have a bunch of other warps that perform additions, and those only take 4 clock cycles. And then the scheduler is able to effectively hide all the arithmetic behind the memory access. And you can imagine the more warps you have in flight, the more effective this latency hiding paradigm becomes. Because when all the warps actually perform memory accesses, then you cannot really hide latency here. And for that reason, it's with those current execution models, it's actually advised that you generally have lots of computations that your threads perform so that you can effectively hide them behind memory accesses. So, and when I'm saying context switch, when we discussed context switches, when we talked about CPU architectures, we learned that those are actually pretty heavyweight. Like a context switch on the CPU would see the thread scheduler basically take all the thread state, copy it to registers, and then when that copy happened, the scheduler would be able to schedule another thread in that core. And that, of course, would not be very effective. And on the GPU, therefore, context switches are really lightweight. And this is what makes this whole execution model actually so viable, that threads and context switches are so lightweight. And this basically only works by not actually copying state to registers. But instead, when the GPU performs a context switch, what really happens is that the state of the warp stays in the same registers that it was before. Like the warp will be set to inactive, but the whole state stays in the same registers that were also used in order to execute the instructions. Like the warp, for instance, like performed like a few, like an addition and a multiplication, and then encountered that the result needs to be stored. And when the context switch happens, all that local state that was used to execute those instructions isn't really flushed out, but stays in those registers. And that means we just need a boatload of registers, right? And therefore, like, registers and register files on GPUs are just huge. Like, they usually go into the tens of megabytes even. And this is most notable, that there are so many registers. And this is actually the only way that context switches can be implemented so efficiently on GPUs. And that, on the other hand, also means that register allocation really is a complex optimization problem. Like, the scheduler will have to make sure that the warps make good use of the available registers, because the more registers an individual warp uses, the fewer warps can actually be scheduled at the same time. And therefore, registers are actually the limiting factor. And the number of registers that a warp uses actually depends on the instructions that are being executed. And those instructions, of course, actually come from the shader. So the programmer, therefore, controls how many registers the program actually uses. And this is what a GPU developer has to optimize for. So the GPU developer will use tools and profilers that will tell them how many registers their shaders and their compute kernels use, and then they will optimize their programs so that they use a minimum number of registers in order so that the GPU can make better use of the register file and can schedule more warps at the same time. And this is basically the execution model of GPUs nowadays. And the terminology I used here was a bit specific to NVIDIA, but other vendors, at least AMD, they work relatively similar. Like, certain vendors have execution models where SIMD is more explicit, but this whole concept is actually pretty similar on other architectures too. And as a matter of fact, what I just described is not only valid for vertex processing, like we are currently discussing the vertex stage of the graphics pipeline, but it is also true for fragment processing, because we have those unified shader architectures, and the same processors are also being used for other types of shaders, like, for instance, fragment shaders. So to summarize this, and based on NVIDIA architectures, there's what NVIDIA calls a processor cluster, and before I called that a vertex processor. And they're just groups of cores, and those groups of cores, they can process vertices in batches, and they usually do so using groups of threads called warps by NVIDIA. They're executed in lockstep, and during lockstep execution, when the thread group encounters a branch, and there are threads that don't participate in that branch, then they have to wait. And the scheduler will always schedule a whole warp at once. And then the scheduler can do this trick where, when there is a warp that waits for, for instance, for memory, or performs another latency intensive operation, then the scheduler can basically set that warp to an inactive state, and then in the meantime can schedule other warps that perform arithmetic instructions, for instance. And that only works because switching between warps is so fast, and because the state of the warps is stored in registers. Like NVIDIA's Kepler architecture, for instance, they have they have 4 of those processor clusters, and each of those processor clusters has 192 cores, 192 shader cores, and then there are 4 warp schedulers per cluster. And from that, you can imagine how many threads, when the occupancy is high enough, how many threads can be scheduled at the same time. And the whole principle here is based on latency hiding. The warp only ever executes a handful, 2 or 4, or on that order, number of instructions on the shader core. And the GPU performs that trick where whenever there is a read from memory, for instance, the scheduler will at the same time schedule arithmetic instructions to hide the latency. And as I said, with those unified shader architectures, the scheduling and the execution logic that is just described is the same on both the vertex and on the fragment stage. And then when the vertex stage finishes, the output finally will be vertices in normalized device coordinates. So at least this is what is prescribed by the algorithm, like what the fixed function pipeline would do. And of course, there are vertex shaders, so the developer is relatively free to perform like other transformations. But then in the end, anyway, the vertices will go through the viewport transformation, and therefore there are like certain assumptions being made to what a vertex shader will do, so in order to make the behavior consistent here. And yeah, as I said, there are other pipeline stages that potentially generate more geometry, and they will, of course, also work in conjunction with the vertex stage, that's for sure, but we will just not discuss them during this lecture. And what follows after the vertex stage is the so-called primitive assembly phase, and we already talked about primitive assembly when I introduced the rasterization algorithm, so we already have an understanding what's going on there. So what's going on there on the one hand is that during primitive assembly, like we're now no longer operating on the stream of vertices, but the stream of vertices is being combined. And the vertex stream is basically combined based on what is in the index buffer. Like, and when the index buffer, for instance, says that pairs of vertices form a line, then we handle that differently than as we would, for instance, handle polygons or triangles or single points. Again, those primitive points and lines, they're actually pretty simple, and potentially those also go through different functional units and different execution modes than the polygons that we'll discuss. But we will focus on polygons actually, and in particular we will also focus on triangles, because when we have polygons, we can just tessellate them into triangles, and in all likelihood this is also what the GPU does. So on the one hand, during primitive assembly, we now use the index buffer to reproduce the connectivity of the vertex stream. And on the other hand, we also perform culling and clipping. That is, we have to make sure that we only take those vertices into account that are inside the visible frustum, and that also results in the input primitives, that is in the triangles, like being clipped against the visible frustum. And like obviously this is quite easy for triangles that are fully inside or that are fully outside the frustum. And triangles that straddle the bounding planes of the frustum, those triangles require special handling. And this part of the pipeline is, of course, not documented so well because the vendors don't really publish those internal details. But there are like a few strategies that are like conceivably can be used in order to implement that clipping phase. And the first approach is the obvious one, like where you really use a like a real clipping algorithm, such as the Cohen-Sutherland algorithm, for instance, and where you basically perform the clipping operations in object space. Like this would be executed for each and every triangle and would like result in the potentially 7 triangles being output from that pipeline that we discussed before. And like this is one possibility to implement this, but it's actually a pretty costly one because algorithms like this, like the actual decision if a triangle is split, is potentially not so bad, but there are other like potential cost factors that come with this. And like there is a second approach where it is conceivable that it is used by the vendors. Like this is of course not documented, but one approach that one could take would be just to use the rasterization pipeline to perform the clipping. And that approach would see us very conservatively identify those triangles where we're really sure they're inside the frustum and identify those that are outside the frustum. Like typical approaches that are used there are like guard bands. Like a very conservative approach that just tells us which triangles are inside and which triangles are outside. And then those corner cases where we just don't know, we perform special handling by really just entering them into the ensuing rasterization stage, into the ensuing scan conversion stage. And there we would scan convert them, but we would do a trick, like we would, in addition to the triangle edges, also add edges for the visible frustum. Like here in this case, with the raster engines, we are in window coordinates, and therefore we can perform the whole clipping operation in 2D, which is of course very beneficial and simplifies things a lot. And if we have those triangles where we are unsure, we would just enter them into the pipeline. And then in addition to that, we would just add 4 additional edge equations. And those are edge equations for the visible frustum that is for the projection of the visible frustum. And then we would let the raster engines perform the clipping operation. And that's of course like a very elegant way to do this. Like this has its merits, but of course it also has its downsides. Like when we only very conservatively identify triangles that are inside and outside, we potentially enter many more triangles into the pipeline that are then eventually clipped, but are there to begin with, so that we have to deal with them on the scan conversion stage. But nevertheless, this idea of entering additional edge equations just for the frustum would be a very elegant one because it wouldn't require any additional hardware. Like, this is of course not documented that the vendors actually do this, so this is just an idea how things could be implemented. But it's conceivable that this is at least a possible implementation. Yeah, and the phase that follows after primitive assembly is the scan conversion phase. And we already talked a lot about the scan conversion phase during the computer graphics part of the lecture, where we talked about Pineda's algorithm. And in general, the scan conversion stage is a non-programmable stage. Like, there are no shaders that we can supply where we can programmatically influence how the execution here is performed. And on this stage, what basically happens is that the stage is provided with triangles as input, like the triangles that are coming from the primitive assembly phase, as we discussed before, and the stage converts those triangles into fragments. And the functional unit that operates on this stage is the so-called raster engine. And the raster engine basically implements a scan conversion algorithm, and nowadays this is usually the algorithm described by Pineda. And then the raster engine has to make a decision when to generate a fragment. Like, this is usually done based on coverage, like on coverage of the raster points that we're testing for. Like, when the raster engine finds that the midpoint of a raster point is being overlapped by the triangle that is tested for, then it will generate a fragment, and otherwise it won't. And we also learned that fragments generally manifest as quads. So in the programmable parts of the pipeline, this is not so obvious. Apart from that, in the fragment shader, we have derivatives available that we can use, for instance, for texture accesses. But other than that, the fragment shader execution doesn't expose that there are fragment quads, but the fragment quad is really the elementary unit of the fragment stage, and therefore the fragment quad is also what is really produced by the raster engines. So the raster engines really produce fragment quads and not individual fragments. And before, like when we passed our input into the pipeline, the input consisted of vertices, and on the primitive assembly stage, we combined that with connectivity information by resolving those buffers and converting the input to the primitive assembly stage into connected primitives. And our vertices, they come with attributes. Like, we learned that there are like a number of fixed function attributes, like normals or texture coordinates, and we also learned that there are potentially user-defined attributes. And those attributes have to be carried along. Like, it's not enough that the raster engines determine if a pixel is covered or if a pixel isn't covered. But in addition, we also need to determine, like, what we eventually want to do when we want to render an image is we want to determine a color for the fragment, and from that we want to derive a color for the pixel. And in order to do so, we require those vertex attributes. And at this stage, like on the scan conversion stage, the attributes, they're interpolated across the triangle. And this, of course, needs to be done with the correct perspective, and therefore the type of interpolation that is used here is barycentric interpolation. And on this stage, what is also usually done is backface culling. Like, when we configured our API to enable backface culling, that means that when there are faces that we watch from behind, that we don't want to see them. That's an optimization, so that's not viable in certain situations, but in some situations it is. Like when we are only watching objects from the outside and the objects are fully opaque, then we don't have to take care of backfaces, and we can just basically exclude them from processing. And this stage is also the one where we perform backface culling, because on this stage we have that very knowledge, like if a triangle is facing towards or away from the camera. And I already said that the most important functional unit on this stage is the raster engine. And typical GPU architectures have like a handful of raster engines, like typically 4 raster engines. Newer architectures might have a couple more, but this is the order of raster engines that typical GPUs have. And like this is a parallel stage. There's not really just one raster engine, so this stage requires parallelization. And on the other hand, this is a stage that exposes way less parallelism than, for instance, the vertex stage or the ensuing fragment stage. Here, and the type of parallelization that usually comes to use is guided by a screen space subdivision. Like a typical approach would be like we have our stream of triangles that comes from the primitive assembly phase, and then we have a handful of raster engines who process those triangles. And then a typical approach would be to just like compute the bounding box or the bounding rectangle of the various triangles. And like in this case here, we fortunately have a relatively big triangle. And then we compute the bounding box, and this gives us the triangle's domain, like the region of screen space that the triangle is guaranteed to overlap. And then we would just subdivide that domain into tiles, like the typical order would be 8 by 8 or something like this. And then we would use those tiles, like we would maybe feed them in a queue and have the raster engines, like the handful of raster engines, process that queue. And by using that queue, which like would be in a priority or a work queue, we would effectively load balance the problem in that like if a certain raster engines would have more work to do because they're like processing a workload that is inside of the triangle, then at the same time the other raster engines could work on tiles that are also in the queue. So we could load balance that using those queues. But nevertheless, what we have here is we have a work redistribution phase from the vertex stage to the rasterization stage. And we're also like kind of relying on the size of the triangles, for instance. Like if we had a triangle that would maybe only overlap a 8 by 8 region, then it would fall into only a single tile, and therefore we would have no parallelism. Like we're generally in a situation where we have a completely different mapping of work to functional units. Like before, we had a mapping where we had a input stream of vertices, and those vertices were processed by vertex processors, and we learned about those warps where we had like massive parallelism inside the warp and inside each core and inside each vertex processor. And the parallelism now is actually quite different. Like we have parallelism over the tiles. We have way fewer functional units. That is, there are way fewer raster engines than there are shader cores. And we have potential load balancing issues that we just didn't have with the vertex phase. Like this is deliberate. Like there are reasons where we performed that subdivision of the algorithm. When we discussed the algorithm rasterization 2, we very deliberately chopped that algorithm into phases. And one phase is the rasterization phase, but we're now very explicitly subdividing those phases, and because of that, we don't suffer from load imbalances on stages where we don't have to. Like the load imbalances from the rasterization stage don't carry over to, for instance, the vertex stage or to the fragment stage. And that, of course, on the other hand, poses the difficulty that we now have to deal with potential load imbalances. And in order to handle those load balances on the GPU, there are like dedicated functional units that are concerned with redistributing the work. Like NVIDIA calls this a work distribution crossbar. And the work distribution crossbar or the work distribution unit basically takes the output from the primitive assembly phase and reorders it and distributes it to a handful of raster engines. Yeah, and a typical architecture and data flow would look something like this, where you have like what I'm colloquially calling the geometry stage here in this diagram, which is basically just the vertex stage and the primitive assembly stage. And those stages output triangles and triangle edges that are input to the work distribution crossbar, like the functional unit that is responsible for distributing work to the raster engines. And then we have our raster engines like basically processing the work that is redistributed from the crossbar. And we already saw how load balancing would be implemented with raster engines. And a possible way of optimizing things a little bit is like, and GPUs actually employ this optimization, is to have like shallow hierarchies of raster engines. Like, for instance, we would have a raster engine that is responsible for only culling tiles. Like, for instance, this tile here in the upper left corner can be effectively culled by performing rasterization for two corners, right? For two of the extreme corners. And if both of those corners are outside of the triangle, then we know that the whole tile is outside of the triangle. And GPUs on this rasterization stage quite often employ some type of hierarchical work distribution. So this is quite typical. And on the other hand, it's also quite typical that those are like really shallow hierarchies. Like, a hierarchy is of course beneficial in that it would be able to identify lots of work a priori and cull larger workloads from actually being processed by the raster engines that are concerned with individual tiles. So this, of course, is a asymptotic and an algorithmical optimization, but on the other hand, it's also something that makes the hardware more complicated. Like, when we put this to the extreme, we would have like a tree traversal over raster engines, and this is of course also not feasible, and therefore GPUs quite often employ very shallow hierarchies where we have like macro tiles, so to say, and those macro tiles are processed by dedicated raster engines, and only if a tile is really known to be inside the triangle in regards to what the raster engine that is responsible for the macro tile found out, we process it further with one of the raster engines on the lower level. So this is actually quite typical that raster engines are organized hierarchically, and it's on the other hand quite typically that those hierarchies are very shallow and very simple, and that the hierarchy is basically hard coded into the actual hardware. So, and I already said that with this type of design, like with a screen space distribution of the domain of the triangle, small triangles are actually quite problematic. And we can see that this is even more problematic with this type of design where we have a hierarchical work distribution among the raster engines, like where one raster engine is responsible for the upper level and four raster engines are responsible for processing tiles. Like, when, say, we have a triangle that falls within a single tile, then we would have the top level raster engine perform work only to find out that the tile is occupied by the triangle, and then the work would be dispatched to one of the bottom level raster engines. And if we have like many small triangles, this would like usually be the case, and this is one reason why we really want to avoid small triangles. And like, it's actually pretty similar to what we learned about acceleration data structures for ray tracing. Like, when we discussed ray tracing, we talked about uniform grids being a potential acceleration data structure for 3D models. And then we learned about this teapot in a stadium problem, where the teapot is somewhere inside that model, and the model in and of itself would be relatively coarse, but we have this complex teapot like somewhere in the middle, and the size of the macro cells of the uniform grid being adapted to the overall size of the relatively coarse 3D model, and then we would have the teapot basically falling into a single cell, and that basically defeating the purpose. And this is the same thing that can happen here. Like, this can load to quite a lot of load imbalances, and this can even become more problematic if we basically use those hierarchical grids. Like, this is actually what it is. Like, what we basically have here is a hierarchical grid. Like, the two macro tiles form a grid, and inside each of those grid cells there's just another grid. And those types of data structures can be quite effective if we have a relatively homogeneous workload. and they can be quite ineffective and quite inefficient actually when we have workloads that are heterogeneous. And in particular, on GPUs, that would mean that we have many small triangles. And what's actually even worse is when we have like lots of small triangles and we also have like a couple of large triangles and we have a combination of the two. And as a matter of fact, small triangles can actually be problematic for other reasons. Like take for instance this illustration here where we have a relatively small triangle and it actually overlaps three fragments. And unfortunately, it just overlaps three fragments that are all part of a different fragment quad. And this would then eventually result in three fragment quads being generated, and thus in 12 fragments. And that would also lead to 12 executions of the fragment shader. And this, of course, is also problematic. Also, in general, there's always been this advice that it's a good idea to avoid small triangles in a rasterization-based pipeline. So we now know how the scan conversion stage works on a conceptual level. And the scan conversion stage is precluded by the primitive assembly stage. And in between those two, there is a phase that is called triangle setup. Like the primitive assembly stage will generate triangles, and then in between, there is a conversion of those triangles to edge equations, and it's a bit fuzzy where this part of the pipeline actually belongs. Like it's somewhere in between the primitive assembly and the scan conversion stages. And here the triangles are basically just converted to edge equations. And then on the triangle setup stage or in the triangle setup phase, what also happens is that those edges are evaluated. Like the triangle setup phase will pick out certain reference points and evaluate the edge equations for those. Like this will typically align with the tiles that we saw earlier. Like the triangle setup phase will take the edge equations that were just computed and evaluate them for certain reference points, like for instance the minimum point of each tile. And those will just be passed on to the raster engines. So the task that the raster engines perform is actually pretty lightweight. Like with one of the edge equations evaluated, computing the value of the edge equation for all the other raster points inside the tile is basically just a interpolation process. So this is very lightweight. And this is what is done during the triangle setup phase that actually prepares the input data for processing in the raster engines. And from that, you can you already have an idea how simple a raster engine actually is. Like the logic behind a raster engine is actually a very, very lightweight logic. So the raster engine performs the Pineda algorithm, and we discussed the Pineda algorithm in some detail during the computer graphics part of the lecture. And the Pineda algorithm is also a subject of the exercises. And we, on the one hand, determine visibility with the Pineda algorithm. That is, we determine if the triangle actually covers the raster points that we're evaluating for. And on the one hand, we have like several attributes that we have to interpolate over the triangle's surface. And we already learned that we're now in a 2.5D coordinate system. So the depth coordinate of the triangle actually is an attribute, like a value between 0 and 1. And the triangle coordinate system is actually more like a 2D Cartesian coordinate system. And so the raster engine is not only responsible for determining visibility and to write a binary value into the raster data structure that stores the output from the scan conversion phase, but it is also responsible for interpolating vertex attributes over the triangle's surface. And this is done using barycentric interpolation. And it is discussed in the exercises how that actually works and how barycentric coordinates relate to the edge equations of the Pineda algorithm and how the edge equations can basically be used directly in order to interpolate those attributes. But it is important to note that depth is also an attribute, and that on this stage, during the scan conversion stage, we also interpolate the various vertex attributes, and this gives us interpolated values for each of the generated fragments. So, and then finally, there's one thing that needs to be said about the scan conversion stage. And so we discussed in quite some length that the rasterization algorithm performs the scan conversion phase, and this is followed by the fragment phase, and only then will we determine if a fragment is actually visible, like if it is obscured by other fragments that are in front. And the argument here was basically that we want to support semi-transparent geometry in our pipeline. And in order to do so, we have to delay the depth test, like the execution of the depth test, until the very end of the pipeline. And this is actually only true to some extent, because as a matter of fact, the GPU vendors actually employ quite a number of optimizations, and one of those optimizations is the so-called early z-test or early depth test. And the responsibility of the early depth test is actually to compute visibility before the fragment shader is executed. And when we have a look into the OpenGL specification, it says there that the OpenGL specification states that these operations happen after fragment processing, meaning the operations that have to do with visibility computation. And then it goes on that, however, a specification only defines apparent behavior. So the implementation is only required to behave as if it happened afterward. Therefore, an implementation is free to apply early fragment tests, and the fragment shader being used does not do anything that would impact the results of those tests. And that in particular means that the vendors intercept the fragment shader and then will analyze what the fragment shader does. Again, when the fragment shader discards fragments, or when the fragment shader assigns alpha values that are below 1, that means that we really have to do late z-tests. And otherwise, like if the fragment shader will not manipulate the depth of the fragment and will not discard it and will only assign opaque colors to the fragments, that means that we can actually decide visibility early on. And this is actually what the vendors do. Like when the driver and the runtime find out that the fragment shader will only ever produce opaque geometry, then we can perform the depth test early, and the vendors actually make use of this optimization. And this is really due to the fact that the OpenGL specification only specifies apparent behavior and not what really happens inside the pipeline. And this is important to keep in mind, like in particular when we're programming, like when we are writing a fragment shader and we tamper with the depth of the fragments, which is sometimes necessary. But if we don't have to, then we really shouldn't, because with that we would effectively disable the early z-test optimization. And it also shows us that, like, we talked a lot about theory and how in theory algorithms like deferred shading work and the theory of the algorithm in general. And we also see that the vendors find quite pragmatic solutions, like really inspecting the source code that the application developer wrote in order to find out if the depth is really manipulated or if it isn't. And if it wasn't, then we can make use of these early tests in order to avoid quite a lot of computation to be performed during the fragment stage. Yeah, and as said, the early z-test optimization is an optimization that the GPU tries to apply before the fragment shader is executed. And it's something that is really not exposed by the APIs. Like the API will not allow us to flip a switch to turn early z-test on and off. But we can influence if early z-test is used by the language constructs that we use inside the fragment shader. Like if we do anything inside the fragment shader that tampers with the fragment's depth, then we actually also tamper with the visibility of the fragment, and this will, on most architectures, cause the early Z optimization to be disabled. This is just important to keep in mind. So, and there's actually another reason why it's a good idea for the vendors to implement the early z-test on the scan conversion stage. And the reason is that the raster engines basically work on tiles of what will later become fragments. And this gives the vendor the opportunity to cull like a whole tile, like perform this decision, this visibility decision, not only for single fragments, but for a whole tile of fragments before even processing them. And if this opportunity exists, that's of course quite efficient. Like if this decision can be performed for a whole tile, this is more efficient than during the fragment stage later deciding if single fragments are visible or if they are covered by other fragments. And this is another reason why the vendors take the opportunity to use this very stage to perform culling of whole titles of fragments. So with that, we're like basically halfway through the pipeline. Like the scan conversion stage of the pipeline is basically where we go from the geometry level to the raster point level. Like the next stage of the pipeline will work in the window coordinate system and will work on fragments. And the two remaining stages that we're going to discuss are the fragment stage and are the render output stage. And in the next session, when we start discussing those, when it comes to the discussion of the render output stage, we'll also have a discussion that is a bit more algorithmical. Like we will discuss compression algorithms that come to use on this very stage. And those are some of the topics of our next session. See you then.